Hello everyone. Today we are going to talk about local average treatment effect late. So let's start with an empirical motivation. So economists like to estimate the return to education, right? So we run this kind of regression here. We regress earnings or wage on education, and one problem is that we know the OLS estimate is likely biased up because of the ability bias. And there's likely some correlation between education and the error term. So economists use instrument to fix the ability bias. However, we find that the IV estimates tend to be greater than the OLS estimates in the literature, which is pretty bizarre and counterintuitive, right? Because we expect that the IV estimates to be smaller than the OLS estimate if they successfully fix the ability bias. Right, here are some potential answers. Why is that? We already see from Angus and Kruger, right, the return to education seems to be from the IV estimate seems to be larger, but that's not just in that particular paper. It's actually pretty common in the literature, and that's why people needed to think about why is that. So the first answer is maybe because of the measurement error, right? The measurement error can cause downward bias in the OLS estimates, and if the instrument fixes the measurement errors, then the IV estimate could be larger than the OLS. So let's see. Let's say we have a noisy measure x star, which is the true x plus some random noise. And for simplicity, we assume epsilon is uncorrelated with any other variable, anything. Okay. So that's the setting of what we call classical measurement error. So the error is just a random noise. And let's just get some more space. So we know the probability limit of the OLS estimate will be the covariance x star y variance x star, which will be covariance x y, right? Because epsilon is uncorrelated with anything, including y, including y, which is x beta plus u, and the denominator will be variance x plus the variance of epsilon. Right? So as you can see, so will be the probability limit of the OLS estimate if x is measured with error, if there's some measurement error in x. You can see that this guy actually is less than beta. Right? So even though the noise is purely random, measurement error can cause downward bias in the OLS estimates. Okay, and like we mentioned, so the IV estimate can actually fix that. If you have another measure of x, let's call x prime, which is x plus let's say e. So if you have another measure of x, which is also measured with error, let's say X star is husband's reported household income. X prime is wife's reported household income. If you just use husband's reported income or wife's reported income, run a regression, the OLS estimate will be biased down. But if you use like X prime as an instrument for X star or vice versa, you can show that the IV estimate is actually consistent. And so we know that the IV estimate can fix the downward bias in the OLS estimates when there is measurement error. Okay, and you can try to do it yourself. It's actually very simple. Just show that. Actually, if we just get some more space here, you can just try to show that beta IV is actually the probability limit of beta IV. Let's say we use X star as an instrument for X prime. And you can show this guy actually will be consistent. Okay, so the second reason is what we call the publication bias. So if you remember, IV or two-stage least square estimates are less efficient. They have larger standard errors than the OLS. Right. So to get statistical significance, say 5% level, your point estimate needs to be at least twice large than the estimated standard errors. Right. And because journals likely only publish statistical significant results, so we only observe those estimates that are twice larger than the we only observe the estimates for return to education that are twice larger than the standard errors. Okay. So in only paper with large IV estimates get published, and that's why we tend to see IV estimates are larger than the OLS, right? Because for the OLS estimates to be significant, you don't need it to be that large, right? But for the IV estimates, because it's not very efficient, so you actually need a larger point estimate in order to get statistical significance. And because only these results get published, we have a biased results. Not biased result. We only observe part of the distribution. Okay. So that's something we call publication bias. Okay, so basically it's like say, okay, so that maybe the true distribution of beta IV are like this, but somehow we only observe this kind of estimates because only they are large enough to be statistically significant, and so we thought the IV estimates or return to education are larger than the OLS estimates. A third potential reason is just bad instrument. Right, like if you use father's education as an instrument for children's education, it is very endogenous. Right? So you may have endogenous instrument, or you may have very weak instrument, or you may have some finite sample bias, like we talk about the Enquist and Kruger paper. There's actually a very, very good paper, a very famous paper. But even in that paper, there's some concerns that their instrument may be weak and there may be finite sample bias. So like I said, find a good instrument is actually very, very difficult. So one reason could be just a lot of these estimates are not reliable. Okay. Okay, so the last potential reason is heterogeneous responses. Maybe the OLS estimates and the IV estimates capture different population parameters. So recall that the parameter in general could be random variables, right? And in general, the true model should be something like a random coefficient model here. Your return to, because we know that there's definitely heterogeneity in return to education, right? Your return to education and my return to education are not the same, right? Although we model that as a beta concept, but we know in reality that, well, we hope our estimate is some sort of average. We probably get some sort of average return to education, because we know that in reality, different people have different return to education. And here it's saying maybe the IV estimates are indeed correct, consistent, but they just capture different population parameters. They just capture maybe just the IV estimate may only capture a subgroup of people's return to education. And we're going to talk about that here. But to talk about the heterogeneous responses, we need a more general framework. Okay, so here we're going to talk about the treatment effect framework. So let's start with a binary treatment, 0 and 1. Let's say, think about going to university or not. A very simple treatment. The outcome variable, you can think about like earnings, and we can write down outcome variable like this. Right, so it's clear. So yi will equals 1 when di equals 1, yi equals 0. Sorry. yi equals y1i when di equals 1, and equals y0i when di equals 0. Okay, so what is y1i? So y1i is the value of yi when di equals 1. y0i is the value of yi when di equals 0. It's just the definition. So you can think about y1i is the earning if you go to university. y0i is the earning if you don't go to university. Okay. And note that for each individual I, we can only observe one of the variable, but not both, right? For you guys, I can only observe your y1i, your earnings with a university degree. I cannot observe your earnings without a university degree. So I can only observe your y1i, but I cannot observe your y0i. And the one that is not observed is called the counterfactual. So for you guys, your counterfactual is your earnings without a university degree. With the framework here, we can easily define the causal effects, right? So if we want to know the causal effects of going to university, that's very straightforward, right? That's just y1i minus y0i. And obviously that's the treatment effect is different for each person, right? Okay, so because there's no way to estimate beta I, right? Beta I has a distribution, and there's no way to estimate each beta I because it's different for each person, and we only observe either y1i or y0i for a person, so there's no way to estimate the beta I. But we may be able to estimate something like the average. So we call that the average treatment effect. There are also, and we can also define something like average treatment effect on the treated, the ATT. So that's the mean of beta I given di equals 1. And similarly, we can define ATUT, average treatment effect on the untreated. That's the mean of beta I given di equals 0. Okay. And in general, AT, the average treatment effect, ATT, and ATUT, they are all different. And we can write down the relationship here, right? So we know the average treatment effect is the probability, the average treatment effect equals to the probability of di equals 1 being treated times the ATT plus the probability of di equals 0 being untreated times the average treatment effect on the untreated. Right. So it's just the weighted average of, so the average treatment effect is the weighted average of ATT and ATUT. But in general, ATT, ATUT, and AT, they are all different. They are all different number. Okay, so note that this is our yi, right? We can actually write down yi as a function of beta I and di, right? So, and that looks almost like a regression model. So in fact, we can still interpret our beta I as a slope, and the ATE, the average treatment effect, is the slope over the entire population. The ATT and ATUT is a slope over the subset of population, right? The ATT is the slope over the subset of population that their di equals 1, the subset of population that are treated. Okay, so now we want to work out what the OLS estimates in this case in the general framework. Okay, so note that here we haven't made any assumption, right? We haven't made any assumption regarding whether the treatment is exogenous or endogenous. Okay, so let's see what the OLS looks at. What is the probability limit of the OLS estimator looks like? Okay, so we know the OLS estimator looks like, the probability limit by definition is like this, right? That's just the conditional mean of yi given di equals 1 minus conditional mean of yi given di is equals 0. That's just by definition, because, well, yi equals alpha I plus beta I di. And alpha I is just y0i. Right. So then we plug in, so we know yi equals y1i when di equals 1, yi equals y0i when di is equals 0. Then we do a small trick here. Because, well, they're conditional on different things, right? This guy conditional on di equals 1, this guy conditional on di equals 0. We cannot combine them. We cannot do calculation here. So we need to do a small trick. So we insert something is 0, but this thing is like conditional on di equals 1. So we can combine them together here. So we have this, the mean of y1i minus y0i condition on di equals 1, which we know is the ATT, average treatment effect on the treated. And we have the second term here. That's the something we call the selection bias of ATT. Okay. So the OLS estimates gives us, in general, without making any assumption, the OLS estimate gives us ATT plus the selection bias, right? And the selection bias is unlikely to be 0, right? Because look at here. So people who go to university, their earnings without a university degree is unlikely to be the same as people who don't go to university. It's unlikely to be the same the earnings of people who don't go to university, right? And that's why we call selection bias, right? Because here we acknowledge that people may select into the treatment. People may select into going to university. So their outcome, so this one is actually counterfactual for people who go to university. Their outcomes may be quite different, right? So you cannot simply use people who don't go to universities, their Y0I as a counter. Sorry. So you cannot simply use Y0I, the observed earnings of people who don't go to university, as a counterfactual or for people who go to university, right? Because their Y0I may be quite different from these people, right? People who go to university, their earnings without the university degree may be very different from the earnings of people who don't go to university. That's the selection bias. Okay, so that's how in the treatment effect literature, the framework here, we show that the OLS in general is biased. Okay. Right. So in general, the OLS estimates give you the ATT and the selection bias. Okay. Alternatively, you can also show that the OLS also converge in probability to the ATUT plus the selection bias of ATUT. Right? You can just do another trick in the middle, and you can easily show that the OLS estimate also give you ATUT plus the selection bias. So in general, the OLS estimate is converged to this guy here, right? The ATT plus bias and the ATUT plus bias, right? And in general, ATT may not be the same as ATUT, and so the bias could be quite different as well. So if there's no selection bias, then the OLS will consistently estimate the ATT and the ATUT, right? So in what case? Well, we know that if, say, for example, your DI is independent, that could be the case if you have a randomized control experiment, then you will have unbiased estimate. And in fact, your OLS estimate will be the average treatment effect and will be ATT and ATUT. And they will be all the same. Right? So that's why if you read empirical work, only when people running a randomized control experiment, they will say that the treatment effect represent the average treatment effect. That's the only case you can say that your OLS estimate will give you the average treatment effect. And the reason is because if you have a randomized control experiment, there's no bias, and ATT will equals ATUT, and will equals the average treatment effect, because ATE is simply a weighted average of these two. Okay, so that's a special case. Another special case is like, well, if beta I is indeed a constant, right? So that's actually our linear model, right? In the linear model, so far we assume that's a constant. And now you can see why that's actually a very strong assumption. Right. But if let's say beta I is indeed a constant, so the treatment effect is homogeneous. And if we are willing to assume exogeneity assumption, basically the OLS1 assumption we already made before, then we can show that the OLS converge to beta, and in that case, again, AT equals ATT equals ATUT. Because we already assumed there's no heterogeneity, beta I is simply a constant. Okay. Right, so basically, yeah, so if you rewrite alpha I equals alpha bar plus ui, where alpha bar is the mean of alpha I, we can rewrite yi equals alpha I plus beta I di as alpha bar plus beta bar di plus ui. So it's just like our original linear model, right? Then if you are willing to make the assumption that the covariance diui is 0, they are uncorrelated, we can show that the OLS estimate is converge in probability to beta hat, and that beta bar, and that will equals ATE and ATT and ATUT. Okay, so now let's talk about late. Okay, so that's from a famous paper by Imbens and Engris in 1994. Okay, so let's start with a special case again. So let's say the treatment is homogeneous. The treatment effect is homogeneous, right? So we can write down yi as a linear model. And suppose that if we have an instrument that is exogenous and relevant, then again, you can show that just like the previous case OLS here, you can easily show that here the IV estimate converge to the true beta bar here. Okay. And if we also restrict the instrument to be binary, you can show that, okay, this guy here will be the probability limit of an IV estimate, right? And this is something we call the wall estimate. Okay, so that's actually the simplest form of an IV estimate, right? So the numerator is that guy here is what we call, if you remember, this is essentially regress y on z, so this is we call reduced form. And the denominator is we regress the endogenous variable on the instrument. So this is something we call the first stage, right? So if you remember, yes, the beta IV is the ratio of reduced form over the first stage. And the wall estimate is the simplest form because the IV is also a binary variable. Okay. Okay, so now we are going to work through the wall estimate to show that what is local average treatment effects. Okay, so let's back to the general case. So yi equals alpha I plus beta I di. And if you want, we can rewrite alpha I as alpha bar plus ui. But the beta I is still a random variable. Okay, it's a random variable. Okay, so you need to be careful. Beta I now is a random variable. So, okay, so this is Wall estimate, right? This is the probability limit of the IV estimates. And if we plug in yi here, okay, so we got the alpha I here and beta I here. Okay. Okay. And if the instrument is valid, so it's uncorrelated with UI, or let's say in general, let's assume that ZI, the instrument, is actually independent. So we know the first term will be 0, right? This guy will be 0 because that's just the equals. So which equals 0, right? Because is 0, right? Because if the instrument is uncorrelated with UI, then this guy should be 0. Okay. So we can show that, okay, so the alpha I actually will be 0. So the IV estimate, its probability limit will be the guy here. We have beta I di and di. Right? We cannot simply take beta I out here because beta I is a random variable. Right? So beta I is a random variable, so we cannot take beta I out. So okay, so here let's talk about the assumption of the local average term effect. The first assumption is ZI, the instrument, is an independent instrument. So it's independent of both yi and y0i, and therefore it's independent from beta I, the causal effect, the treatment effect. And we need the instrument to be relevant, so Zi is correlated with Di. And we are going to write down Di just like the way we write down Yi. So Di equals D1i times Zi when Zi equals 1, and D plus D0i times 1 minus Zi. So we know Di equals D1i when Zi equals 1. And di equals d0i when Zi equals 0. The second assumption is new. So this is the second assumption is called monotonicity. It needs so d1i greater or equal to d0i, and the probability of that is greater than 0. It seems a bit confusing, but let's take a look here. So note that there are actually only 4 combinations of D1i and D0i. The first one is something we call always taker. So for the always takers, their D1i and D0i both equals to 0. So Di equals 1 regardless of Ci. So no matter what the instrument looks like, they are always going to be treated. For example, you can think about these are people who will always stay in high school, regardless of whether they were born in first quarter or born in later quarters. And similarly, we will have never taker, so there D1i and D0i will always be 0, regardless Zi. right? You can think about the people who will always drop out high school, right? And regardless whether they were born in the earlier quarter or born in later quarters, right? So their di0 equals 0. Their di treatment always equals 0 regardless of the instrument Zi. And complier, so compliers is people who compliers their di equals 1 when and d0i equals 0. So they will be treated if Zi equals 1. They will not be treated if Zi equals 0. Right. So these are actually people affected by the instrument. Right. So these are people who will drop out high school if they were born in earlier quarters, but they will stay in high school if they were born in later quarters. Okay. And we will also have defiers. So defiers are very strange. Those are people whose d1i equals 0, d0i equals 1. They are opposite to complier, and that doesn't make much sense. So the monotonicity actually rule out defier. Right. So that's those are defiers are people who choose to stay in high school if they were born in later quarters, and they will drop out high school. They will stay in high school if they were born in earlier quarter, and they will drop out high school if they were born in later quarter. So that's very strange because the monotonicity will rule out these defiers. Oh, and note that in general, we cannot observe from the data. There's no direct way to say, oh, this person is a complier, this person is a always taker, and this person is never taker. There's no way to distinguish them. Okay. Because for a person, you see, okay, the person born in first quarter, and so the person born in first quarter and decide to drop out, the person could be either complier or never takers, right? And for a person who born in later quarter and continue high school, they could be always taker or complier, right? So they are actually mixed together. Okay, so now let's take a look about the probability limit of the IV estimates. Right, so again, we know we start with this guy. Right, so we already deal with alpha I. Now we need to deal with beta I di. Okay. So because Zi equals 1, so we know the first term will become beta I d1i. The second term will become beta I d0i. Similar for the denominator, it will be d1i and d0i. Right, so that will be here. Because we already take out the condition, so we can actually here we can even combine then the numerator together. So we will have expectation of beta I times d1i minus d0i, similar for the denominator. So for the numerator and denominator, we both have d1i minus d0i. Okay, now note that so note that d1i and d0i is a binary variable. There's only 4 combinations, so and d1i and minus d0i is actually a binary variable. Right, because d1i minus d0i is either 1 or 0. And because of that, so we can rewrite the expectation as a probability, right? So the expectation of a binary variable equals equals to a probability, right? The expectation of a binary variable is just its probability. So that's the probability of d1i minus the d0i equals 1. And that will equals probability d1i greater than d0i. Right? Because d1i equals either 1 or 0, d0i equals 1 or 0. Right. So the probability that d1i minus d0i is 1 means d1i is the same as the probability that d1i equals greater than d0i. So what's the case? So that means actually means d1i needs to be 1 and d0i needs to be 0. That's the only case we have that d1i greater than d0i. Okay. So we can simplify the thing here, right? So we know we can simplify the thing here. We just replace the expectation here by probability, and we rewrite the numerator as a conditional expectation again times the probability. So, and then we can actually even cancel out the probability here. So we show that the beta IV, the IV estimate converge in probability to the expectation of beta I given d1i greater than d0i. And that is the complier, right? We know that because we already rule out defier, so the case that d1i strictly greater than d0i means these are complier. So these are the causal effect or treatment effect among the complier. And that's why we call that local average treatment effect. So what we show here is, in general, if your instrument is valid, you get the local average treatment effect, right? So your IV estimates gives you the conditional mean of beta I among the compliers. Right, and of course, in general, we know the local average treatment effect is different from average treatment effect or average treatment effect on the treated, and also different from the average treatment effect. Right, because the average treatment effect is among all population. This is among all people being treated. But here, essentially, the local average treatment effect say, when you use the instrument, we only add, even if your instrument is perfect, we can only estimate the causal effect among people whose behaviors are affected by the instrument. Okay, which actually is very intuitive, right? Of course, if you use instrument, you can only consistently estimate the causal effect among people who are affected by the instrument, right? If you use a quarter of births as instrument, you can only estimate the return to education for people whose behavior are changed because of quarter of births, right? You cannot estimate the return to education for OS taker, obviously, because their effects are not affected by the instrument, right? Like we actually already talked about, intuitively, the instrument throughout the variation, and only keep the instrument is throughout some variation and throughout endogenous variation, but it's also throughout some exogenous variation, right? When you use an instrument, the instrument, because of the first stage, right? So if you remember, the IV estimate is a reduced form over the first stage. So essentially, you only keep people whose behavior, whose X are correlated with the instrument, right? So therefore, even if your instrument is perfect, you can only estimate the causal effect among those people whose X are correlated with the instrument. So that's why intuitively this is how we intuitively we can only estimate the local average treatment effect. We are not able to estimate like ATT or ATE. Okay, so now we are going to use this to explain why the IV estimates for returns to education tend to be greater than the OS. Okay, so it's a standard figure, right? So we have a downward sloping return to education. So that's actually the marginal. So the marginal benefit of schooling, and let's say we have. Sorry. So, and let's say we have two type of people: low ability people and high ability people. So for all low ability people, their marginal cost of schooling is higher than high ability people. Right. So, just say the marginal cost is higher for low ability people because it's more painful for them to sit in the classroom and to study, right? So their marginal cost is higher. But let's say for these two type of people, their return to education actually the same. Right? The marginal benefit is the same. And we know, so therefore, people will maximize their utility where marginal benefit equals marginal cost, right? So for low ability people, the model shows that they will choose low level of schooling. For high ability people, they will choose high level of schooling. And that's actually the standard model, human capital model, to explain why there's different levels of schooling, right? But note that, so in principle, we know the OLS is like, so the OLS estimate is roughly the average. I'll probably give you roughly the average. Let's say this is, sorry. So let's say this is the average, right? And the OLS may be a bit upward bias, so give you somewhere here. Right, so the OLS estimate is capture the average treatment effect or average treatment effect on the treated plus some bias, right? So it's, let's say it's somewhere around here. But then if you use instrument and you can imagine that people whose dropout decision is purely because caused by their quarter bursts, they are likely to be low ability people. And for if we consistently estimate the return to education for these low ability people, then our IV is likely to be at here. Right, and that's why that is likely greater than the OLS estimate, even though the OLS estimate is likely biased, but our estimates of return to education using quarter bursts or other instrument, if they may be larger than the OLS estimate because we capture return to education among low ability people. Right, because their marginal return for low ability people, their marginal return to education actually higher than the overall average, even plus some bias. Right, the OLS is overall average or average among average plus some bias. Okay, so another application of a local average treatment effect is the regression discontinuity. And we are going to talk about the regression discontinuity a bit later. So let's stop here.